G'day, in this video we are looking at Einstein's mass-energy equivalence. It's our final dot point for the module 7.4.4. We're looking at how the behavior of light affects how we understand time, space, but particularly today, matter and energy. Einstein's mass-energy equivalence is the relationship E equals mc squared. Today, our focus is on understanding what this equation actually means and what it implies and what the consequences are. And we're going to begin looking at least one example where this is demonstrated. So some learning intentions for this lesson is that we're going to have a look at special relativity and how it connects to Einstein's mass-energy equivalence. We're going to look at some scenarios where we can observe this equivalence and account for mass to energy conversions or transformations in a variety of scenarios. The interesting thing about this dot point is it exists here because Einstein's mass-energy equivalence is connected to special relativity. However, we're not really going to be looking at the applications of the mass-energy equivalence until Module 8. And so the idea of today's lesson is to introduce these concepts and make some connections to special relativity and use that as a springboard to be able to apply Einstein's mass-energy equivalence when we get to Module 8. This dot point is kind of the transition point, if you will, between Module 7 and Module 8. Therefore, if there's elements of the syllabus dot point that we don't cover today, we're going to be doing that more throughout the remainder of the course where it's contextually appropriate. So the mass-energy equivalence equation. This accounts for the transformation of mass to energy and energy to mass, which, just like everything else that we've been looking at in this inquiry question, is not particularly intuitive because in the everyday, it is not something that we really experience or observe. But energy is able to transform into mass, and mass is able to transform into energy under certain specific circumstances. E is referred to as the rest energy. This is the energy that the particle has when it is at rest. So this is not the kinetic energy that the particle has. It's got nothing to do with temperature. It's essentially all of the energy that is stored inside the particle due to it having mass in the first place. If that mass was to convert into energy, how much energy would be released? M is therefore the mass of the particle, and C is the speed of light. And so the rate at which energy converts into mass is connected to the square of the speed of light, which is the constant that makes this equation work. So the connection between special relativity and the mass-energy equivalence is actually quite complex. And for the sake of simplicity in this video, it's not a concept that I'm going to dig into particularly deeply at all. We are going to talk about it because this dot point does exist in Module 7 and Inquiry Question 4 in particular, which is all about special relativity. But when you actually read the dot point, it doesn't allude to the fact that you need to understand the connection at all. Rather, the dot point asks you to apply the mass-energy equivalence relationship, which is in particular going to be very important in Module 8. As such, we're going to go through it in class. There's a video that I'm going to use that's been done by Minute Physics and provides a scenario where you can kind of get a derivation kind of happening to show where E equals mc squared comes from. We're not going to do it for our flipped classroom video. Instead, I'm going to move on and focus on how we can actually apply the energy mass equivalence. Today, we're going to be observing this mass energy equivalence in the nuclear fission of uranium. The concept of nuclear reactions is something that we're going to unpack in much more detail moving into Module 8. It's not content that we've covered yet, but to understand the mass energy equivalence, we need to be looking at a process that we haven't dug into just yet. So I'm going to kind of be talking and coaching you through a lot of the concepts. If you don't fully understand it today, it is not the end of the world. We will certainly revisit this in Module 8. In any case, we have this uranium here, uranium-235, which is made of 235 protons and neutrons, 92 of which are protons. If you were to shoot a neutron at that uranium-235, you would then have uranium-236. It's picked up an additional neutron. But this nucleus is what we call unstable. Because it's unstable, it likes to break. It undergoes fission. Fission implies that there is a cracking or a breaking up of, and that's exactly what happens. We form a barium atom, a krypton atom, and 3 neutrons. What you'll notice is that the total number of protons and neutrons is the same every time. 1 plus 235 makes 236, and so does 144 plus 89 plus 3 individual neutrons. every time we get 236, which means that there is a conservation of mass. Additionally, there is a conservation of the protons as well. In each step of this fission process, there are 92 protons present. So on the surface, it looks like the law of conservation of mass has been accounted for. However, if we dig a little bit deeper into the reactants, the products, and their masses, we'll actually see that it's not quite so simple. Here we have a table with the masses of a bunch of different reactants and products, and the masses are written in unified atomic mass units. What they are and where they come from and all that kind of stuff isn't too important for today's lesson. We just need to know that we're not, measuring our masses in kilos or anything like that. So our reactant mass for our uranium-235 and our neutron is 235.044 plus 1.009, and that gives us 236.053. If we were then to add up the mass of our products right at the end, the barium, the krypton, and the neutrons, we find that their masses are 140.908, 91.905, and 3 lots of 1.009 respectively. And when you add them up, we get 235.85 atomic mass units. We should notice straight away that these two totals are different, and that difference is exactly equal to 0.213 atomic mass units. We call this a mass defect. Through this nuclear reaction, what has happened is that there has been a loss of mass from the starting matter to the ending matter that forms. So where has this mass gone? Well, essentially, this mass defect has been caused by the conversion or transformation of this mass into energy by E equals mc squared, which you could quite easily calculate for. All you would need to do is multiply the mass in kilos, there's a conversion that we can use to do that, by the speed of light square. This energy transformation is mostly observed in the fact that the particles that are the products of fission have a bunch of kinetic energy, and when they split apart, they do so with a very large amount of energy. And it is this energy which causes a chain reaction for the nuclear fission of uranium. The 3 neutrons which are expelled at such a speed that they are able to interact with other uranium particles and cause the same fission process. Again, where did this energy come from? Well, it came from the mass defect. By E equals mc squared, this loss of mass led to a transformation of kinetic energy, which ended up in the neutrons as well as the other fission products as well, but within the neutrons, giving the neutrons enough energy to be able to continue the reaction. There will be multiple points in Module 8, particularly towards the end, where we will look at other scenarios where E equals mc squared is applicable. We're going to be looking at different kinds of nuclear reactions that occur on Earth, nuclear reactions that occur in the sun, which lead to their release of energy that we, live and survive on, as well as some particle-antiparticle interactions, which we'll look at right at the end. So this is not the only time that you're going to be looking at Einstein's mass energy equivalence, but instead it is the first, and as I said earlier, is just meant to be an introduction today. And that brings us to the end of Module 7 and opens us up to really dig deep into some quite interesting concepts that we'll look at in Module 8. But until then, have a good one.